Welcome to the lecture about autonomous robotics in the Introduction to Artificial Intelligence course. So if you think about what comes to mind when you hear the word robot, I think many of you will immediately have an idea. I Googled that word beginning of this last year and got this on the first page. Not surprising, all of these are humanoids, right? Anthropomorphic robots. And that's pretty much the kind of the idea we have about robotics from literature. The origin of that word actually comes from human-like, come to life animated object. You will see a little later some legged robots, some vehicles, some robot arms, compliant arms. Actually, there are no industrial robots on the first couple of pages, even though, of course, industrial robots are really what exists in reality. But a lot more industrial robots are working in the world today than humanoids or other autonomous kinds of robots. You could say fundamentally, all factory automation is a form of robotics, which is traditionally then defined as programmable machines, so machines that are flexible in what they can do, and that flexibility shows up in them being programmable, a whole continuum of actions being possible. If you look up a textbook like the one I cite here on classical robotics, you will see topics that relate to that. So it's about how to describe mechanically robot arms and robot vehicles, so-called degrees of freedom problem or configuration space. It's about the kind of motions these artifacts, these manipulators make, rigid body motion, about their kinematics forward and inverse, so computing where they will be in space or computing what kind of joint angles to make to come to those positions, their dynamics, physical dynamics, trajectory formation, which means designing the time courses of the movements and the paths, motion planning, controlling these, so making sure that they actually do follow those plans, and maybe there's something about grasping sometimes and something about controlling wheeled robots. So the only topic among those that overlaps with artificial intelligence research is really the motion planning trajectory formation topic. And so I will not be really talking about these kinds of topics. Just want to make sure that is actually where the bulk of classical robotics is. So in artificial intelligence, we're more interested in autonomous robotics. So autonomous really means that they program themselves in some sense, right? The word comes from this Greek notion of nomos, giving yourself the law, autonomous. And technically, we mean by that these robots generate some form of behavior, some form of movement, ultimately action, that's based on sensory information that they themselves have acquired, they are informed about what correct actions or desired actions are based on their own perception of the environment. And so if you remember my first lecture in this series about cognition, and then you see that that's very much aligned with the vision of artificial intelligence. I then quoted from the textbook of Russell and Norvig that the idea of an intelligent agent is a unifying theme in artificial intelligence. And they even define artificial intelligence as the study of agents that receive percepts from the environment and perform actions. So that's the definition essentially of a autonomous robot. And it's maybe the only question is whether the agent really has to be physically able to act, or would it be acting just informationally, for instance, by talking to someone or giving some response on a computer screen. So this notion of organizing one's behavior based on sensory information that is acquired by the robot is, of course, in contradiction with the classical robots that are programmed, and they're programmed based on information about the world that is available to the programmer, not to the robot itself, to the robot system. Even though a industrial robot will also have something that's called autonomous control, which is essentially to make sure that it really physically realizes the planned motion, the programmed motion, and it does that based on sensory feedback, for instance, shaft encoders, kind of sensors about its speed and position, and it will control by reducing the deviation between the plan and the real state. So that form of autonomous control is not what we mean by autonomous robotics. In autonomous robotics, we expect something more, something not as simple as that, as just achieving a set value. And one way to talk about that is to say we are looking at systems, autonomous control systems that also make decisions. So decisions ultimately in the simplest form mean that some graded change in sensor information will lead to qualitative change, macroscopic change. So a very simple example would be, if you autonomously avoid an obstacle, there will be a critical point when you will decide autonomously if you avoid it around the left or around the right. A small difference in sensor information will lead to that macroscopic difference. Or, you might want to orient your action to one object rather than another, depending maybe on how closely they match the description. There will be some critical point when you switch your preference to another object, and that would reflect that you have made some macroscopic decision. There are many more complex ways to talk about that, and those are essentially the ways to talk about cognition, as I did in my first lecture. So cognition as revealing a more indirect link, or systems become more cognitive the more indirect the link between their sensing and their acting. And the decision would be sort of the first milestone in becoming indirect, where the input doesn't uniquely determine the output. Memory would be another one, and sequences and so on. So clearly that's the, to demarcate autonomous robotics from control. In the opposite limit case, we also actually don't really think of autonomous robots as being totally free to do whatever they want in a way, right? And concretely, that means that we typically expect these robots to take commands, to do tasks that we instruct them about by giving them some kind of orders. And in fact, here's a demonstration of someone, Johannes Stusefies at the Institute did this work a long time ago, where he interacts with a robot, giving verbal commands, pointing at objects, and the robot will do things then. And so that is actually a very plausible use case in which the autonomy is essentially setting up an interface. So you still program the robot, but you program it now at a high level by talking to the robot with human language, maybe with gesture, both immersed in a shared environment, an assistant robot. And autonomy then consists of the robot filling in the details. When you program the robot in a conventional sense, you would have to give it all the details, where exactly the object is, the coordinates, and which joint configuration exactly to use, with which speed, and so on, which grasp. And being able to just set the goal as this macroscopic level, like get me this object, then the generation of the detailed solution to that would be the autonomous part. So in that sense, autonomous robots could be viewed as robots that provide this kind of high-level communication interface. And that's an idea very common in assistance robotics. I wanted to give you a survey over some typical autonomous robots. Took some images, not all of them are very new, just to make a landscape, and that will prepare one point I'm going to make next. So here, one thing that is commercially available, I actually own this little vacuum cleaner. You can buy those for not very much money now. There's a whole bunch of single task vehicles, and this is not the latest, that do these tasks autonomously with their own sensors and so on. So that is well established. We actually built some of those back then. I'll show you one example of those. So that's sort of a research tool. Then you can have vehicles of other kinds, outdoors, also special tasks. The more special the tasks, the more successful these kind of things. And of course, there's autonomous driving. And autonomous driving, as you will know from the media and so on, has made enormous progress, is becoming close to being feasible in daily life. And it is a form of robotics. It's not always perceived to be that, but by its very nature, it is autonomous robotics. And I'll refer to it a little bit. Most of my survey will not really focus on that, and you'll see why in a moment, but I will be referring to that a couple of times. Another form of vehicle are legged robots, which vehicles also because they move around the world and carrying the sensors along. They are very often inspired by biological analogies, insect-like robots or sort of salamander-like robots, dog-like robots. This is actually a human-like robot. It's also an animal. And they provide a form of locomotion, so they are vehicles in that sense. And they have this advantage of being more flexible with respect to the surface that they walk on. And biological systems, as you know, have not developed wheels. Also, somewhat biologically analogous are some special purpose kind of robots that crawl or can climb or snake-like and so on for special purposes. And then underwater vehicles are commonly looked at as autonomous systems, so inspired by fish, if you wish. It's easy as a medium because it's so homogeneous. It's mostly a communication problem underwater, but it's a legitimate form of autonomous robotics. And then, of course, flying robots, drones, as you know, are now very common. And again, they're autonomous very easy. In fact, commercial airliners are on autopilot very often. In that sense, they are autonomous then. The decision-making, though, is made remotely, and that's one of the frontiers of making these systems autonomous in this wider sense of going beyond control. Now, robotic manipulators or arms or hands are a different story. So they are, in some sense, analogous to industrial robots, but now you're thinking about a robot that is autonomous, for instance, that would perceive an object and then orient its action to an object, grasp it and handle it and so on. And that autonomous part is actually very difficult. So autonomous manipulation is one of the frontiers. It's not very much successful work in that domain. I'll be talking about some of the difficulties. And then you can, actually, we in our research also look at things like that. So here at the bottom, that's one of our systems that is supposed to grasp objects based on its own vision. You just saw that the object was moved around just as it was approaching, and that's one of the features that is able to update its plan. Now here another case, update its plan as it is being as it is acting. And then you can put the arms on a vehicle, and then you have a mobile robot manipulator, and that is also a human interface here that combines all these problems. So get the picture, perhaps, what overall that field is. So why do we do this? Why are we interested in that? I ask people occasionally, including my son, about that, and here are 3 responses I get, which actually do match or line up with some typical use cases. So they are cool, fun systems to have, like all the movies are about that. They could serve me, like serve drinks or clean up the kitchen, or they could be soldiers, without humans then having to do that job. And those are 3 use cases. Actually, useless robots that are toys or for animation or entertainment are actually the first real commercial uses. There's some robots that are sold for that purpose. There are some famous case that some autistic children tend to react better to robots than to humans in some sense, but it's a very niche application. So that's sort of a purpose-free way of using robots. It's very popular in Asia for some reason, in Japan in particular. The other big vision that's very popular in Europe is the vision of assistance robots. So robots that work at the home or in the workplace collaborate with humans. It's very demanding. So a lot of problems need to be solved to do it. And I'll talk about some of those problems later. It's not a reality. It's a research enterprise. And the military robotics exists as a big field that is not so well known because most of the work is confidential or not done in universities, for instance. It's ideal as a technical application in that the need to remove humans from the scene is obvious, and the environment is difficult. We call that natural, hard to model, could change. So could be hostile. Various kind of threats you have to detect and so on. So it's ideal for this kind of research. And there is much research on that in Europe. It's not as much as in the US and probably in Russia and China. As a side aspect, this is often the opportunity for people to think about robot ethics, which shows up in robots that act autonomously only, right? Because then you have decisions being taken, and are these decisions subject to some kind of ethics? So in the military case, people ask, can you, is it admissible to have a robot decide autonomously whether it opens fire or not? There are actually already Navy vessels that are conventional, but they are in some sense robotic, autonomous, when they are in a certain mode of battle configuration where there's a human who can override commands, but they a priori decide autonomously, for instance, to shoot an anti-aircraft missile. That's been around for decades, actually. So these issues are real. As we look at autonomous driving, issues like that come up. For instance, if you detect a possible collision with a pedestrian, on the other hand, that an evasive maneuver might lead to a crash, which are going to do prefer the owner who bought the car, maybe it's your customer, or do you have some value hierarchy built in? So there's a lot of debate about that, and there's some interesting work by philosophers, for instance, about work like that. So ultimately it's a question of offloading decisions from the user to ultimately to the designer. The robot is autonomous, but it does that it makes the decisions according to what the designer provided as an algorithm for making those decisions. And so there's interesting debates about that. I'm not going to go deeper into that, but just point at that. And then there are vehicles, of course, which didn't really follow those three purposes. Vehicles are for driving, right? For autonomous transport, and that's a very obvious service they provide, so that one doesn't even think twice about whether that's useful. So the use case for autonomous vehicles is actually the best. And that's also one reason why they are very advanced. There's an example from Amazon, who has these little vehicles, these little red things under the shelves. Those are robots. They're only minimally autonomous because they will detect obstacles and then just stop if there's an obstacle, and then send to base the command that there's a problem. Other than that, the plan of how they move in the warehouse, that's all centrally controlled. So based on sensor information that's not available to the robot itself. But still, it's sort of a minimal form of that. That's a very much expanding area. But then, of course, autonomous driving of cars, on roads, that's the other big use case. So that's an obvious reason why one does that. Now, the actual reason why a lot of us are doing autonomous robotics is really that it is an ideal playground for research. And I want to substantiate that interpretation a little bit. So one idea in autonomous robotics is that it is a challenge to the basic paradigm of modern engineering. Could say, roughly speaking, modern, I'm not talking just last 50 years, engineering really is based on modeling systems, having very good approaches how to model objects and the plant itself that you control and so on. With everything that is not modeled then being treated as stochastic. So you've modeled every deterministic aspect, and we have very good theory for that, including some exact theories. And autonomous robots act in environments, we call them natural environments, even though they can be factory and so on. And that really just means they're difficult to model. And so you'll see that's fundamentally pushing the envelope of this classical paradigm. And some people react to that by saying we have to try harder to model even that. That's, for instance, done in probabilistic approaches. And others argue, and I'll see that in a little while, that maybe one can achieve some things without modeling everything. So that's a fundamental challenge that robots enable you to work on. Another related aspect is that modern engineering is very much based on modular design. So modular design means that you build components, modules, which interact with other modules in some well-defined way, in a limited way. And that means that you can localize problems. You don't have to redesign your subsystem whenever something else in the system changes or is updated or things like that. And autonomous robots tend to require a lot of close kind of integration. I'll mention an example like that in a moment. And therefore they challenge this. So system integration is very important, and they challenge this modular view, even though modular design is still a goal in most of autonomous robotics. In fact, autonomous robotics is a very interdisciplinary field within engineering. I've listed here some of the necessary components that you'll have to deal with, and I have actually only listed here things that are related in a wide sense to AI kinds of problems, sensing, perception, which is really making use of sensory information to estimate something about the world, to classify objects, to map the world. The mechanical design, which often is thought of being part of the solution, which can be intelligent, adapted to the task. Control, of course, AI, algorithms of planning, embedded computing, doing all those things on a platform with limited resources. Communication among processes and with the user, data security issues there, user interfaces, human factor issues and so on. So there's a lot of different disciplines that are all integrated on a single platform. And what I didn't mention is some of things like energetic autonomy. There's very interesting stuff about that. If you have outdoors, you have all the resistance to temperature and weather, and a lot of other things that it's very interesting as a research field. So that's a little bit why we do that as a drive, and I'll be, of course, focusing largely now on the research perspective. I'm not going to give you a state of the art in terms of benchmarks and performance, but I just want to give you a little bit of a feeling of kinds of approaches. Really just be talking about two approaches that are commonly used in designing autonomous robots. So the classical vision dates back to the beginnings of autonomous robotics as a field, as a serious field, not a sort of playground. It started in the 50s. Shaky was maybe the first serious effort. And these systems had what is called the Sense Plan Act architecture. So roughly speaking, they had modules of function that would follow the sensory stream from the sensors to ultimately the actuators in different modules, and that allowed, again, to modularize function along that stream. You could say the sense and the act part are, control and sensory information, signal theory kind of problems that were sort of like in conventional robots or in other areas of engineering, so shared with those, not specific to autonomous robotics. While the AI part, the intelligent part, was sort of focused here at or localized here at the center. So the model, which would be sometimes called the world model, which essentially entail perception, that is extracting from sense information about the world and then building maps of the world in that way. And based on these maps, planning actions that would entail, for instance, a whole sequence of different individual actions that would lead to a goal. With the goals, it's not really represented explicitly here where they come from. They would be essentially parameters of the plan, and they might have to be acquired from somewhere or be set by the programmer. So I want to say a few things about these two levels here, the model level, which entails perception and mapping, and the planning level. So perception is, of course, critical to autonomous robotics, as I defined it, acting based on your own sensory information, and what that actually means based on your own perception, because what you do in perception is extract information about the environment. It's not, so perception is sometimes misconstrued as being estimating the stimulus. That's something like image processing. That's not actually what perception is. It's about extract information about the environment. In my lecture about cognition a couple weeks ago, I elaborated on that point, and you might want to remember that. So here, if you look at a scene like that, what your perception as a human will be about is about objects. You will be perceiving that scene, maybe the setting of the scene, but you will largely be perceiving the objects in there, and pay less attention to this picture as a picture, as except if you want to maybe paint it or so. So you will, for instance, attend to particular objects maybe if you have a task in mind, like you want to drink a glass of water, maybe you will look for the water and you will be able to find it in the scene and select that, essentially bring that into the foreground. You will be able to recognize this as a glass and other elements here, classify them. You might, for instance, see that this is a piece of a pretzel, even though it's kind of broken off. It's not actually a complete pretzel, but maybe you're able to see that. And so that would be an example of invariance under an important form of transformation. You will be able to estimate things. For instance, you can grasp these objects, and that means you can estimate their pose, compute how far they are, maybe in which orientation you would have to grasp them, and so on. And you will even segment objects in the sense you will know which part of the image pertain to the objects and which not, so where the boundaries are in the image. Here, this glass is very interesting, right? You can clearly see this wine glass here, even though it is transparent, and use the visual structure behind it. So that's a very challenging segmentation task to know which pixel here is foreground, which is background, right? Because you see the background through the glass, but we're very good at that. That's a real challenge for computer vision. So that's object-oriented vision, which I want to contrast to the kind of perception that may underlie spatial orientation. So for instance, you could have taken this image at some point, and you want to now, when you're there at in that same area someday later, use that image to compare it to your current view and then say, am I at the right spot? Some of you might recognize where that actually is, and this does involve recognition matching, namely matching, for instance, different images which are under different lighting conditions, different weather situations, slightly different positions. You want to estimate the position from that. So that is ultimately how navigation, how estimating where you are works. It doesn't always work with images. You can have other kinds of sensory readings, often just depth profiles from a laser rangefinder, for instance. But matching past information to current information to recognize that you're at the same location is sort of the core operation of using sensory information to estimate your spatial location or orientation. And you see that requires matching with some invariance. Like here you might have to say, well, this corresponds to that and this corresponds to that, and so on. So there's some invariance because it looks different in these different cases because of the lighting condition and some metric transformation. And from that, you can then estimate, for instance, your pose. It does not require necessarily object attention. I was just, drawing your attention to things, but that's just to guide your human performance. But you could do this with just the whole image, the whole array. For instance, a lot of that is done in navigation of vehicles, where you take the depth profile and just match the depth profile. And you don't have to talk about objects in there. And certainly you don't have to segment the scene into different portions. You don't have to really say this is the lake and there are trees and so on. That doesn't really matter for that matching. So the demands on perception for essentially estimating ego position are quite different, as you've seen. They are actually less sophisticated. There are things that lower animals do and that simpler algorithms can do. And that is one of the reasons why autonomous vehicles have made more progress than autonomous manipulators. So manipulators orienting the action at objects, while vehicles essentially just need to know where they are, and then they might have to do a little bit of object orientation in the sense of maybe seeing the road, but you can even navigate based on just a compass and a direction. So a lot of these demands for orientation can be actually met by low-level sensors. Distance sensors are often considered then. They are low-level, for instance, just a single signal, the depth signal, and maybe in terms of their ecology, so what they reveal about the environment, they are actually also very invariant. That is, if you have a laser rangefinder, it will tell you the distance, no matter what material or what the lighting conditions are or the weather is, and so on. So that's been a big source of progress in the vehicle domain, that with low-level sensors, you were able to solve these orientation problems. Yeah, maybe that's here. There's a famous problem called SLAM, self-localization map formation, that essentially combines the map making with this form of estimation. So what you're trying to do is, as you drive around, you're trying to take your low-level sensor information, store it, and make, therefore, the locations at which you acquired it recognizable when you come back to those locations. And from that, you want to build a map yourself, while always, and the mapping based on your own estimate of where you are. And that's been an area that's made a lot of progress, essentially through what is called probabilistic thinking, or probabilistic methods, which I'm not going to elaborate on in this lecture. Sebastian Thun is a famous researcher in that area. There's a group of 3 German fellows, Dieter Fox, Sebastian Thun, and Burkhardt, I can't remember his first name, who made a major contribution with these probabilistic approaches and pushed that field far ahead. So some people even consider that solved. There are a lot of practical problems to how to actually pull that off. This has very large demands on storage and in some cases on computation, but there's considerable progress in this area. So much about mapping and perception. Last word I want to say that so the more extended idea of this would be that what was called a semantic map, that is, at different locations in the map, you also recognize objects now and really acquire meaning, therefore, about the objects. And that, of course, entails then these much more difficult problems. And that's a topic of current research. So planning is an interesting field. There's a lot of literature on mathematical methods of planning that is based on having world models, often world models that are mathematically idealized, for instance, like these polygonal surface maps, where you would describe objects and areas in the air by polygons, which is difficult to really obtain from sensor information. But if you have it, there are very good mathematical approaches. Classical, it dates back to the 90s and early 2000s. Some of these are computationally still expensive to achieve. So solving a path in higher dimensions when you have a complex robot arm problem can be computationally demanding, so that even today, to do that in real time can be hard. And some people build special purpose processors to solve motion planning problems. And motion planning is still a very active topic of research. At robotic conferences, you will have often the largest sector of contributions will be in the motor planning, movement planning domain. But I would say it's a mature field with a lot of techniques, and its problem is for largely having that world map. Tobias Glasmacher has lectured about an aspect of planning which wasn't exactly path planning, which is sort of like a sampling of that literature. It's important AI literature. For instance, a lot of this planning is using search algorithms, minimization of some kind, and then reinforcement learning. So I don't want to go deeper into that, but I want to say, so this was all in sense plan act picture. I want to say that this, the major difficulty for that has been obtaining these maps, the world knowledge, having these representations of the world, largely when it entails really knowing about objects. So in the 80s, late 80s and 90s, an alternative approach was developed. It's not a single approach, it's sort of an alternative way of thinking was developed that sometimes runs under the label of behavior-based approach. Rodney Brooks is a apostle of that. He made it very popular, and he also contributed to that, his so-called subsumption architecture. There are various different forms of that. I'll mention Ronald Arkin in a moment. So the idea was we need to get rid of that world model. And one problem with the world model is that it is sort of general, that all the behaviors can take the same world model, and say instead in nervous systems, we see there are specialized behaviors, and these behaviors have access to special channels of central information. It's actually, even in the human, you could say, for instance, a what and where system in some sense. And so, for instance, information about spatial location, orientation is achieved by a special path that doesn't actually have the same complexity as the path that supports recognition, for instance. And so in this view, you would build the robot from a bunch of different behaviors, and each behavior has its own special purpose sensory input and acts on motors. and they would be quite restrained with respect to how they interact. In some proposals, they can only activate each other. Sometimes they can what is called subsume, that is to provide the input to another module or get the input from another model behavior, sorry. So to avoid to have the same architecture problem again, just between these objects. And that is, I mean, it was a very successful approach. It led to a real breakthrough in that simple special purpose robots became feasible with simple sensors. And these examples of the robots I showed you at the beginning, the simple special purpose robots, you can buy in any electronics store now, or it's in a commercial store. Those are all sort of inspired by these kind of ideas, even though they're now already much more complex than that. The limits of that also appeared quickly. That is, they do not really scale to more complex tasks that require longer term planning, especially they are essentially just basing usually their behavior on the sensory information immediately available. And that's why they are something called reactive, and so they don't have really plans. This is actually a little demo that we did a long time ago. The electronics of this is the Lego robot. It was at the time not yet available from Lego. It's an electronic kit one could put on one's own little robot. And it's an example of a robot that is extremely simple in terms of its internal algorithm. It's based on dynamical systems, but in a adequately structured environment, it seeks out sources of light in a way that looks intelligent in some sense, but it's all just reactive. It's very, very low level. So these kinds of approaches have not gone away. They are very influential as a sort of a basic level, sometimes called the reactive layer of robot architectures. Very many approaches use those, and they essentially say that for the fine control locally of movement, especially of vehicles, but also of arms, we will rely on special purpose sensory information that solves these tasks in a very special way, and not rely on having a world map of everything. So here's an example from an architect also older, where there is a reactive layer that an architect called schema controller, but sort of the same kind of idea. And then there would be more conventional sense, plan, act systems with also learning and user interface components that then act onto the robot through that reactive layer. And that's very common. It's sometimes called a hybrid architectures because it combines these so-called subsymbolic and the sense, plan, act kind of approaches. And that's sort of the state of the art today. You will have many systems like that. And a lot of the autonomous driving algorithms actually have some kind of architecture like that, a low reactive planner, and then planners with longer and longer planning horizon, and that make more demands on sensory information and mapping. Good. So I want to close or come to the end of this video by talking about core challenges that remain challenges. Some of those I already mentioned, but they remain research challenges that really severely limit what autonomous robots can really do. And they are very interesting research challenges. So I'll mention 4 of those, 2 of which are very related. So I already mentioned perception, of course. And I say it was originally the big crisis. The World Sense Plan Act, the world model was just so hard to come by. Still frontiers. The progress has been very limited. I mentioned in the vehicle domain, there are these special shortcuts, much simpler there, but in object-oriented action, which is the basis for more interesting behavior, this is still a frontier. So there was a period when computer vision was not used much. This, the laser rangefinder, the vehicle research was very successful, but people have come back partly because computer vision has made a lot of progress, in part based on deep networks and other machine learning approaches, in part also just because of the scaling of computing power and generally on learning ideas. Currently, there's a lot of so-called end-to-end deep learning. So we just raw images and you take some raw control output, and just brute force learning with a lot of time and resources. That is being criticized in the robotic community about its lack of usefulness, the invariance. For instance, when you change the visual environment, you don't want to relearn all the control and so on, but is certainly a strong research enterprise in that direction. There's one fundamental difference between robotic vision and a lot of the computer vision that is used in strong alliance with machine learning, in that in robot vision, you typically have only a limited set of objects in your working environments. The classes of objects you deal with and maybe the concrete exemplars will be limited in nature, but you'll have a lot of experience with these objects. While a lot of the computer vision algorithms are based on having limited experience in just single images or small clips with many, many, many different objects. And these many objects would essentially explore all the variants, and then you extract the invariant component that helps you classify and maybe estimate. That means that the assumptions of these algorithms are not necessarily valid in the case of robot vision. So that's one of the challenges of that. Okay, I don't want to go too deeply into that. Mention that interact with a human user overlaps in part, sorry, I have that word twice here, overlaps in part with the problem of perception, in the sense that when the user interacts with the robot, it interacts about that referred environment and refers that shared environment and refers to the environment, for instance, by language, for instance, or pointing or other things like that. And that will mean that the robot has to perceptually ground the language. And that's harder than one thinks. In my lecture on cognition, I did elaborate on this example on showing how cognitive that is, how you have to potentially test hypotheses and reject some. And there's some real understanding of world properties to do that. And it's a bit misleading in part in that computer vision with machine learning has achieved things like that. For instance, Google does all this work on searching for images by typing in words, and it would then be able to find images that match those words. In the past, doing that very trivially, just based on matching to words that were around the figure in the source where that figure came from. But increasingly, they have algorithms of how to analyze the images and associate them with words. But that still doesn't mean actually that these algorithms know what they see, know about the world. They just find some associations. There's certain images are best associated with certain words, maybe certain parts of images as well. So this is a challenge, and there's a lot of work on that. For instance, attentional algorithms, things like that. So it's an interesting field. And of course, then there's also the aspect of, so that's just the perceptual aspect of grounding language, and language being supportive of communication. And then you have to do things like understand what the intention of the user is. And that's partly a linguistic problem, understanding the meaning of sentences and the pragmatics, what the user wants. And partly there is some form of embodiment in here, in that there is the user attends to something. You might want to find out what that user is attending to based on gaze, maybe based on body posture, based on the recent history, predict what the user is going to be about. And then there's a whole aspect of engaging in dialogue, of actual real communication. And there have been a lot of demonstrations of systems that fool a human into thinking somebody does dialogue, but that's just this scratching the surface, because that's just sort of playing, but doing a dialogue to actually achieve something together, to work toward a goal, is actually quite subtle. And a little challenge for you, if you ever work with someone, like you load a truck, let's say you're moving your apartment, and with someone you carry the furniture. Pay attention to what you're doing. That's amazing how much communication there is physical, where you don't have to explain exactly how to grasp the couch and how to turn it, where there's a lot of looking. You look at a place and the other one knows, I have to look at that corner and maybe lift that up, or by your body posture, you suggest a certain way of doing things. It's very interesting. That is very hard to emulate. There's some serious work on that. Good. This entails sometimes physical interaction. So for instance, jointly acting on an object with a human, or actually directly physically interacting with a human, like guiding a human and so on. And that is a big research frontier that is not so related currently to machine learning techniques, even though maybe it could be. And it's a little misleading sometimes. Modern control theory is very, very sophisticated. It's mathematically very well elaborated, and with modern computing can be implemented. And in some sense, a really enormous level of sophistication. But at its core, there is a problem. It's could be summarized as the lack of robustness in control. It goes back to the theorem that comes from the 70s that essentially says that if you have a small deviation of reality from the model, there is always a possibility of having an unstable control system. So you cannot actually give a limit beyond which you will always have stable control. And that's a problem because when you physically interact with objects, or worse, with humans, and then your models are going to be perfect. If you're an autonomous robot, right? And then you'll be interacting with objects that you only partially know, and human users are notoriously difficult to model. So you're likely to run into these kinds of robustness problems. And they are not just academic problems. For instance, a lot of people don't realize that all these robots in industry, they do largely contactless tasks, or the contact is very limited. For instance, just grabbing some hook or doing something simple. They are not doing things like milling, right, where you have to have an interaction with the surface and take off a little piece of material in a well-defined form. And the reason for that is that very typically robots go through instabilities as they interact with material like that. For instance, because of the difficulty to control forces or control torque, which is very difficult to do. And so many of these machining operations are done by specialized machines, which are not robots in the usual sense of articulated arms. This means these are specialized. They are mechanically designed to solve the control problem. The German machining industry is famous for developing all these very specialized machines, which they can sell all over the world. And production companies would be happy to replace them by robots, which would be much more versatile and flexible. But that's very hard because of these control problems. And so that's a real problem for autonomous robotics. And if you look deep inside, it is ultimately due to the separation of planning and control. So control is so successful because it is fast and stiff in some sense. So it keeps the error, the deviation from the plan, very small. And that makes it possible to keep the plan, just have a plan and just track it. And no need to update the plan because the error was so large, you now have to replan. And that makes these high demands on perception. So the plans have to be right. For instance, if your plan is slightly off, like you're trying to plan a posture that is slightly inside the actual object, then the robot will destroy the object because it's trying to, with all force, to make the distance from the planned posture small. And if it's kept by interaction with the surface from doing that, it will keep ramping up its torque until it cracks the object. So that also makes these robots very unsafe for humans because of these large forces that are generated in order to keep the error, the deviation from the plan, so small. So in a way, the difficulty of physical interaction is really inherent in the approach that classical control takes. So an alternative that is currently a hot topic in robotics is sometimes called soft robotics, which one I think is inspired by human motor control. Maybe not everyone, maybe it was invented independently. It's certainly true that humans as robots are soft. They are soft in the sense they are compliant, viscoelastic. The muscles are viscoelastic. They're essentially damped springs. And actually all robots are damped springs in some sense, but they're extremely stiff, while the muscles are relatively non-stiff compared to the loads that they can handle. So for instance, when you stand upright, you're an unstable pendulum, right? You would fall over. It's the muscles that on both sides of the body that keep you up. And these muscles are so spring-like, and you could think if these springs are strong enough, so to be to compensate for the inverse pendulum, which is sort of a spring, mathematically speaking, that is unstable, then that would stabilize upright posture. It turns out that the muscles are too weak for that. So what you actually have to do is to send active commands all the time to the muscles to keep you in this balanced position. That's a problem that a classical robot like the Asimo Honda robot doesn't have, because its joints are so stiff by control, it can just passively stand there and will not sway and not fall over, as long as the center of mass is over the foot surface. So when you make actuators compliant like human actuators, you can do that by adjusting control mechanisms or by using physically like springy actuators. Some robots that have little springs inside and tendons, and they would usually they wrap up the tendons rather than contract to charge the spring more or less. Then they can come away, avoid destroying objects, so they don't need to know as much about an object. Once to grasp a glass, they just need to plan a posture somewhere inside the glass, and the spring and all the actuators will then create the force, the compression force that will allow you to hold the glass. And so it doesn't matter as much if you've estimated the surface of this glass so precisely, which in the case of a glass, again, is one of the harder problems, right? Now, the downside of that is if you achieve that, then you have a problem with just regular movement without objects. Making a fast movement with an arm that is so soft is harder. Now it's your arm might overshoot or oscillate, and you have to have very good temporally structured plans that are just right to make now a reasonably fast and precise movement. And that's a topic of that kind of research, how to do that. And that's based on the plans and the control being much more tightly interwoven and more interdependent. So that's a very big area of research. Final topic, background knowledge. This is actually the old nemesis of AI. One of the big problems of classical AI is how to get world knowledge into these intelligent systems. And the classical approach was, of course, to represent knowledge by rules that you could invoke. And it's very hard to code everything you know about the world, or you need to know about the world to achieve a task in terms of rules. And that's particularly true about robotic action, because that entails a lot of world knowledge that is graded, is fuzzy, is not precise. So it's very difficult to formulate as rules. How do you open a door? How, where is the milk is in the fridge? How to grasp a glass versus, maybe a plastic cup versus a spoon, and how hard to press. What kind of grasp will allow you to then do a certain kind of action. Putting something down, that you have to clean the space, and how large an opening you have to make to put an object inside. You can imagine the number of things you need to teach your robot is large and amorphous and difficult to formalize. So it shows up very practically as the problem that whenever you have a robot demonstrating a new thing, like a cooking robot that makes an omelet, that's a whole doctoral thesis to do that, right? And then if you next week try to make a steak, then you have another doctoral thesis, roughly speaking. So there's a problem there. And if you look at robot demonstrations that are around, they are still underwhelming. If you look at robot soccer or look at the DARPA challenge, you see that, first of all, there are special purpose tasks always, and there's a lot of work going into solving these tasks, and they're still not very good at it. And so a large portion of that is that background knowledge. You could say when you build a skill, you enable the robot to have a certain behavior, as in the behavior-based approach, where they build different behaviors. That is sort of background knowledge, because you could say there in these skills is knowledge. I mean, when you learn how to ride a bike, then you have acquired world knowledge about how bikes work, and that takes a lot of time. Or if you learn how to use a typewriter, or if you know how to communicate with others, you have skill, and that builds world knowledge. So that's one approach of how to solve that, and would be a question of having a theory of tasks. What are the sort of skills you want to do? So one approach is reinforcement learning and machine learning. That's certainly the hope that you could build skills that way. It has a terrible problem of the size of the workspaces and the need for the difficulty of generalizing. There's a lot of work into that, using notions of having some primitives or some building modules and so on. So the last lecture in this course by Tobias Glasmachers will be reviewing reinforcement learning. And you will see, I think, from that, I don't know exactly what he'll be lecturing about, that it's certainly very far from being deployable in reality at this time. So this is an open frontier, real challenge. So you see these 4 challenges make this still a very attractive field. It's certainly at the core of the AI enterprise. Even you will see in this course that the topics for which there are solutions where there's a lot of work, especially machine learning, but also some of the classical knowledge-based systems, doesn't overlap so strongly with the problems of robotics, somewhat, but not perfectly. Which I think though reflects that we have still important problems to solve. So autonomous robotics is maybe one of the best challenges for autonomous robotic, for artificial intelligent thinking. And I mean, maybe I close on that by evoking in that image that we do have now machine learning algorithms that can win chess games against world champions, and even the Go champion was defeated by a algorithm. And all kinds of computer games can be won by algorithms. But if you Google robot soccer, you will see how that sucks, how bad that is. So I mean, like a 3-year-old will be much better in handling objects and moving around in the world and so on than any of these robots. And so that shows there is a frontier here of understanding how to generate this autonomous action in an agent that perceives the environment by itself. And that's why we do autonomous robotics. Good. Thank you for watching this video, and I'll see you in the lecture.